Okay, so this part right here is just a refresher on the derivative rules, and I know that these say u in here because we want to be able to take the derivative with the possibility of a composition of functions. In other words, using the chain rule, which I don't know if you know this, but the chain rule is very important. But for now, let's go ahead and change these to x's because we aren't going to be seeing compositions in this section. We will in the next section though, so we'll come back to those with compositions. All right, so this is just a refresher on the derivative rules, okay? So the derivative of the natural log of x is 1 over x. The derivative of e to the x is e to the x. And the derivative of a to the x is natural log of a times a to the x, okay? The reason I'm rewriting those is because I want to write expressions for their integrals, okay? Some formulas for integrals. So if I am looking to integrate 1 over x with respect to x, that's equal to the natural log of x plus c. Now here's something that's a little bit tricky. We have to remember whenever we do an integral of 1 over x, and which results in natural log of x, we have to put absolute value bars around this, okay? The reason is in the function 1 over x, negative numbers exist, okay? We know what the graph of 1 over x looks like. Even though it doesn't exist at 0, it could exist in the negatives, all right? But the natural log of x is restricted to a domain of 0 to infinity, so that's why we put absolute value bars around that x. We don't want to plug in any negative numbers. Okay, and then also if we are integrating e to the x with respect to x, that's e to the x itself plus c. And then I'm going to come down here because I have room. And so if I am integrating a to the x, not u, dx. Okay, so this one, the derivative of a to the x is the natural log of a times a to the x. If I only have a to the x, my antiderivative of that is going to be a to the x. However, I will need to divide by 1 over the natural log of a. So go backwards. Let's take the derivative of this. Move that over a little bit. If I take the derivative of 1 over natural log of a times a to the x, I get 1 over natural log of a times natural log of a times a to the x. And then those would cancel out. So whenever I'm doing an antiderivative, I need to divide by the natural log of a. At this point, it becomes extra important that you remember the derivative formulas correctly because you're going to need to go backwards and remember when to undo parts of that, okay? And really, in the next section, we're going to be doing derivatives and integrals simultaneously, so we really need to make sure we keep these straight, okay? If you need to go back and review some rules, this is a good time to do it. All right, let's look at a couple examples. These involve some of our transcendental just means things that aren't like rational or polynomial functions, meaning like trig functions, inverse trig functions, exponentials, logarithms, all of those grouped together, we call that transcendental. So that's what that meant up at the top. Okay, so we are integrating from 0 to natural log of 5 of e to the x dx. Well, based on this formula, okay, the antiderivative of e to the x is just e to the x, but it's a definite integral, so I don't need a plus c, okay? And I'm evaluating over the interval from 0 to natural log of 5. Okay, and now I evaluate by plugging in my b value first, so e to the natural log of 5 minus, and then I plug in the a value, e to the 0. So e to the natural log of 5 is 5, e to the 0 is 1, and so our answer is 4. Okay, last one of these, we're integrating from 1 to e squared of 3 over x dx. So my antiderivative of 3 over x, well, my formula was the antiderivative of 1 over x, but remember what we said about coefficients, we can actually move those in and out. So I can make this a 1 and just factor that 3 to the front. Okay, another way is you could think of it as multiplying by 1/3 on the outside or on the inside and 3 on the outside because 3 over 3 is just 1. But either way, then that 3 on the inside would cancel out and we have a 3 in front. Okay, so then we have 3 times and then the antiderivative of 1 over x is natural log of the absolute value of x. And then our right bracket, and we're evaluating from 1 to e squared. So we have 3, and again, I'm going to just factor that 3 to the front. And then I'll multiply by 3 at the end. But if you want to do 3 times natural log of this minus 3 times natural log of this, that's fine. Okay, so we have natural log of e squared. I can put absolute value bars here or not. It doesn't really matter because e squared is positive. Minus natural log of, and then again, 1 is positive, so I don't need the absolute value bars. Okay, so this becomes 3 times natural log of e squared is 2. Natural log of 1 is 0, so I get 6. Okay, so that's second fundamental theorem stuff. Let's go back to the first fundamental theorem and look at what happens when we have compositions. I guess I should say the first part of the fundamental theorem, okay, because there's really only one. But some books will say first and second. Some just say, here's the FTC and it has 2 parts. Okay, so the first fundamental theorem says if we take the derivative with respect to x of an accumulation function from any constant to x of f of t dt, we end up with the function that is being accumulated, f of x, okay? But what if instead of just an x here, we had u as a function of x? Okay, so like maybe an x squared or a sine x or something like that. Well, if that's the case, well, how do we handle compositions? You guessed it, we use the chain rule, okay, which I'll remind you is so important that we will seldom again differentiate a function without using it, including if that function happens to be a composition function. All right, so we're taking the derivative with respect to x of this. The derivative of the outside part is going to be f of, and then we're plugging u in. U is the inside part, okay, just like over here, x is the inside part, but then we have to multiply by u prime because of the chain rule. Okay, so we're using the chain rule here, all right? Meaning if there is something else here, that same thing still goes in, but then we have to multiply by the derivative of what's there. What we do not do is we do not multiply by the derivative of f of t, or this inside function. We never take the derivative of this inside function unless we are looking for a second derivative. Okay, so let's do a few examples, and keep in mind other properties could still apply. Okay, so I don't want to, I'm looking for g prime of x. I don't want to find an antiderivative function and then go back and find another derivative function. I just want to use the fundamental theorem, okay? So fundamental theorem says the derivative of this accumulation function is equal to the function being accumulated, which is 2x. And my derivative of g of x is going to be a function in terms of x. It is an x, it is not a t, okay? The fact that there's a t in here has no bearing on the variable for g of x. And if I take the derivative of a function g of x, I get a function g prime of x, which is still a function in terms of x. Okay, now, could I have done that one as finding the antiderivative here, which would be t squared, and then I evaluate that from 3 to x, so I get 3x squared minus 3 times 3 squared, and then I take the derivative of that, and I'm right back to 2x? Yeah, I could, okay, but I don't want to, okay? Or not, sorry, not 3 squared, just t squared. Okay, either way, don't do it. Don't do an antiderivative and then try and take its derivative, because you will have functions where you don't know how to take the antiderivative yet. Okay, this one right here, g of x is an accumulation function again, but instead of going from x or 4 to x, it's going from x to the constant. So we need to switch these and put a negative in front. So it's the opposite of the integral from 4 to x of root c dc. Okay, so now when we take the derivative of that function, we have a negative out in front, and then the derivative of this accumulation function is going to be just root x, okay, the function that is being accumulated. Also, again, it does not matter what constant we start at. Okay, so we're starting at 4 here, start at 3 on the last one, could start at negative 2,000, doesn't matter. Okay, for part C, I have a composition of functions. This is the integral from 3 to x squared. So this is my u, that's my inside function. So when I take the derivative, I take the derivative of the outer part, which is going to be the f part, and I plug u into it. So I get f of u, which is x squared, but then I have to multiply by u prime, which is 2x. For this next one, I again have a composition because I don't just have an x up here, I have e to the 5x. So when I take the derivative, I will be using the chain rule, okay? So g prime of x equals, and then I start by doing f of u. In other words, I'm plugging this, my u value, into my inside function. So I get e to the 5x cubed. I'll write that in 2 steps. So e to the 5x, that whole thing is cubed, minus 4, okay? But then I need to take that whole thing and multiply it by my u prime. The derivative of e to the 5x is 5e to the 5x. Okay, in this case, I can go ahead and simplify this. So this is e to the, if I'm multiplying, 5x times 3 is 15x. Okay, that's not 5x cubed. Okay, I multiply exponents together, so that's 15x. And then I need to multiply that by another 5e to the 5x. So I get 5e to the 20x minus 20e to the 5x. Okay, this last one I have a composition as well, but this function's a little bit different because instead of going from a constant to a variable, it's a variable expression to a variable expression. So I can't use the first part of the fundamental theorem just yet. I need to rewrite this function, okay? Well, if you remember, one of our properties said something about it, it was called something with an interval, but it says that if we are integrating from a to c, that's the same thing as going from a to b plus the integral from b to c. So in other words, I can split this into 2 integrals. One of them is going to go from the natural log of x to, and then I can pick any constant I want. It does not matter. I'm just going to pick a 0, but you could even use the letter a if you wanted, okay, of t to the 5th dt plus the integral from that same point to sine x. Oops. Do that, okay, of t to the 5th dt, all right? And now, this goes from a variable to a constant, so I'm going to flip that upside down and put a negative in front of it. So the opposite of the integral from 0 to natural log of x of t to the 5th dt plus, that one stays the same, 0 to sine x of t to the 5th dt, and now I can take the derivative of this whole function by taking the derivative of both parts. So then that's still equal to the original function g, but then g prime of x becomes the opposite of this quantity, natural log of x to the 5th, times u prime would be the derivative of that, which is 1 over x, okay, plus, and then plugging sine x in, so sine to the 5th of x. I guess I don't need that. Okay, or you could put the quantity sine of x raised to the 5th, but then times u prime, the derivative of the inside, so times cosine x. Once again, I want to remind you, we are not taking the derivative of t to the 5th anywhere. I didn't do 5 times anything to the 4th. Okay, I plugged this into this function and then took the derivative of the u part.